and how we can use the Avogadro's number and molar masses to do various types of calculations. The mole is essentially similar to the idea of a chemist's dozen. A mole is Avogadro's number of some particular object. In this case, it represents 6.02 times 10 to the 23rd. If we had 6.02 times 10 to the 23rd atoms of carbon 12, one of the isotopes of carbon, then we would have a mass of 12 grams. So, turns out that that is a very convenient reference point both for the atomic mass unit and for the mass of a mole. So, the analogy between the mole and the dozen is essentially, why do we have 12 of something and call that a dozen? Well, it turns out that happened to be a convenient number of, say, muffins or rolls or eggs. On the other hand, we have other weird numbers of things that we give unusual names. For example, we may have 144 beakers. That's a kind of not very convenient number, so we call that a gross. And then for exactly the same reasons, the Avogadro's number is a not very convenient number, so we simply turn that into something that we call the mole. Since atoms are so small, we have to have a very large number of atoms to be able to weigh them. Turns out that Avogadro devised an appropriate number to provide a convenient mass of each of the elements. Turns out Avogadro's number is 6.02 times 10 to the 23rd, and so if you happen to have that many atoms of hydrogen, you would have 1 gram of the element hydrogen. Since each of the other elements has a mass that is greater than the mass of a hydrogen atom, therefore, if you have Avogadro's number of atoms of, say, iron, that would be what we call a mole of a particular substance. So if you have 1 mole of iron, that turns out to be the atomic mass of iron in terms of grams. So 1 mole of iron is 55.85 grams. Turns out that if we have a corresponding number of sulfur atoms, then sulfur being smaller than iron, it would have a different mass, even though we have exactly the same number of atoms. So, turns out 1 mole of sulfur is 32.07 grams. Turns out that if we have individual atoms or molecules, we often will discuss the atomic mass of an element, but if we have a molecule, which happens to be a grouping of atoms, then we have to talk about the molecular mass. So this would turn out to be the sum of the atomic masses. Of course, we can use the information from the periodic table, which provides the weighted average of all of the isotopes for a particular element, to then come up with the average atomic mass, and then use those values to calculate the average molecular mass. So, as an example, if we have a carbon dioxide molecule, which is comprised of 1 carbon and 2 oxygens, to determine the molecular mass of this compound in terms of AMUs, we would need to know the atomic mass of carbon, which is a little bit more than 12 AMUs. And in addition to that, we would also have to take into account the atomic mass of an oxygen atom, which is slightly less than 16 AMUs. To come up with the molecular mass, we have to sum the atomic masses together, and so in this case we would have to take the mass of one carbon atom and add 2 times the mass of an oxygen atom, and that comes together to give a molecular mass of 44.095 AMUs. In some cases, compounds are not discrete molecular units, but we often will represent them in terms of a chemical formula. And in this case, something like sodium chloride. It's useful to then determine the so-called formula mass of that particular kind of compound. Again, we need to know the atomic masses of each of the elements in the formula and would add them together to come up with the formula mass for the particular substance. So, as an example, pretty simple substance, sodium chloride. Table salt is 1 sodium atom and 1 chlorine atom. If you look at the periodic table, you would find the atomic masses for each of those elements. If you add those together, you would come up with the formula mass of that particular compound. To determine the molar mass of a substance in terms of the number of grams, if I had 1 mole of that substance, all I would need to do is go to the periodic table and recognize that the atomic masses can also be the number of grams per mole. If I simply sum together all those but use the units of grams per mole, I would have the molar mass of that particular substance. So, as an example, what is the molar mass of carbon dioxide? If I add together all of the atomic masses, 1 carbon atom plus 2 times the oxygen atom's atomic mass, sum that together, that would give me approximately 44 grams per mole for carbon dioxide. Notice that the value is exactly the same as what we previously calculated in terms of atomic mass units, but now the unit is grams per mole. So, that is then a really useful relationship that we can use in lots of other calculations. The molar mass of a substance and the atomic mass units for a substance turn out to be the same values, and so therefore we can roughly say that 1 AMU is the same as 1 gram per mole. Likewise, for carbon dioxide, the formula mass is 44.101 grams per mole. It also has a value of 44.01 AMUs. The general formula for the molar mass of a substance is given here. Molar mass is the mass divided by the number of moles. Turns out the value of the molar mass is a convenient conversion factor between mass and moles. In some cases, the formula for a particular compound will be written to indicate how the atoms are attached to one another, and an example of this is shown here for magnesium nitrate. The formula for magnesium nitrate is Mg parentheses NO3, close the parentheses, and then 2 outside of the parentheses. This indicates that there are 2 of these NO3 groups, the nitrate ions. And so we need to take this into account when we calculate the formula mass of this particular compound. So, to do this calculation, we're going to have 1 magnesium atom, so we need to look up the atomic mass of magnesium, and then add to that 2 times the atomic mass of nitrogen because since there are two nitrates, the two outside of the parentheses would be distributed into both the nitrogen and the oxygen. And then likewise, we need 6 oxygen atoms, the 2 times 3 giving a total of 6 oxygen atoms, and multiply that by the atomic mass of oxygen. This gives us a total for each of the elements, and taking into account all of the significant digits that you get for the atomic masses from the periodic table, we can then add those together, and this provides us with a value of 148.3148. But of course, we wish to do this calculation with only 4 significant digits. So the 1, the 4, the 8, and the 3 are each significant digits, with the 3 being the least significant. The 1, the 4, and the 8 are all insignificant digits, and since the 1 is less than 5, we will not round up the 3, and so the molar mass of magnesium nitrate is 148.3 grams per mole. In other cases, we might have formulas where the connectivity of the atoms is trying to be indicated, and so not all of the atoms will be grouped together. An example of this is for ethanol, the structure of which is shown here. So in this case, there are 2 carbon atoms. One of the carbons has 3 hydrogens. The other one only has 2, but then it's also attached to an oxygen atom, which also is connected to a hydrogen atom. We would write this formula as C2H5OH. We need to account for all of these atoms. There are several ways that we could do this. There are 2 carbons in the formula. We multiply that by the atomic mass of a carbon atom. There are a total of 6 hydrogen atoms, 5 from the hydrogens attached to carbon and 1 from the hydrogen attached to the oxygen. Multiply that by the atomic mass of hydrogen, and there's only 1 oxygen. Multiply that by the atomic mass of oxygen, and do the math. The 2, the 6, and the 1 are all exact numbers. We've counted those, so in fact they will not limit your significant figures. The sig figs come from the atomic masses. And so now we have to add together all of the significant digits, taking into account where the least significant digit is located. For the carbon atoms, we have a digit in the 10,000th place, the 4. In the case of the hydrogen, the digit is 1 place to the right. And for oxygen, it also is the 4 in the 10,000th place. So the common digit is in the 10,000th place when we add these together. And so we need our least significant digit to be the digit that is in the 10,000th place, which is the first of the 4s. So molar mass for ethanol is 46.0684 grams per mole.